leader of a combinatorics group in Barcelona, Spain. Among his honors in recent years, he was a Humboldt Research Fellow. He received a Humboldt Research Award, and he was a von Neumann Professor at Technical University Munich, among others. He is perhaps best known for his fundamental results on the asymptotic number of labeled planar graphs and typical properties of random planar graphs and related subject. Today we'll talk about random planar graphs and beyond. Please welcome Marc Noy.
Good afternoon. It is a real pleasure and an honor to be here, and I wish to thank the organizers not only for the invitation, for how the conference is running so smoothly and so pleasantly for all of us. So here is an overview of my talk. I will start kind of introduction by recalling the classical and basic theory of random graphs, as most of you know. But then I will switch to classes of graphs which are constrained by some global property like regularity or not containing a triangle or being a tree. And then I will move to a topic in which we now have a real good picture and we can say many results. And finally, I will say something about extensions to more general classes of graphs. So here is the basic model of random graphs. You have n vertices and n edges. And then you take the uniform distribution among all graphs with n vertices and n edges. So capital N will be used to denote n choose 2, which is the total possible number of edges you have among n vertices. And this says that, well, among all these possible edges, you choose n. And then you get n edges. So this is the uniform distribution. And then how do you compute probabilities of events? Let's take a very simple example. So which is the probability that vertices 1, 2, 3 span a triangle? Well, you have to count. So this is the denominator, it's the total number of graphs you have. And in the numerator, since 3 edges have been already used for a triangle, well, you must choose n minus 3 among n minus 3. And you make just this simple computation, and if you consider this for n large, this is about m over n divided to the key. Well, of course, there are some events which are more difficult to compute, and then you have to, but essentially, all the time, you are using binomial numbers, and sometimes you have to take more subtle estimates that hold for a certain value of k. Okay? Well, this was the model introduced in the fundamental paper that we all know by Erdogan and Remy in 1960, in which already in this paper they prove many results, but probably the best known, the most spectacular is this famous phase transition phenomenon that says that when the number of edges is small compared to n over 2, and you have to think that n over 2 is when the average degree is 1. So when the average degree is 1, everyone has a chance to be connected to someone else. Then all components are small. Small means of size of most logarithmic, and they are very simple. They are either trees or trees plus one edge. But when n is larger, asymptotically larger, then a unique large component emerges. Well, this is well known, and this is not the topic of today. But just let me tell you that this is the seminal paper, which it's still worth reading after more than 50 years, because you always find new things in this original paper. Now, there is a related model which has been more used because it's easier to compute, which is the binomial model. You have n vertices, but instead of fixing the number of edges, you say, I will draw each edge independently with probability p, right? So this is not uniform as before, because if a graph has n edges, which is the probability of seeing this graph after all these draws, well, it's p to the number of edges 1 minus p to the number of non-edges. It's not uniform, and probabilities of simple events are easier to compute. So which is the probability that 1, 2, 3 span a triangle? Well, you have 3 edges, they have to appear independently, so this is PQ. And these models are similar when the number of edges is about p times n, because if every edge is sampled with probability p independently, the expected number of edges is this p capital N, okay, and it's very close to this. So this gives a good approximation, but technically speaking, they are not the same, and there are some subtleties if you want to go from one model to the other. But suppose we take really this equality here, and we take p equals m over n, then pq is this quantity, and you see, let me see if I get this right, and you see that it really agrees with this quantity here, okay, and it's computed easily. And this is the main point. I mean, there are elementary events regarding degrees or components or cycles which are easy to compute, and this has given rise to a very rich and powerful theory since then, and many in the room have contributed to this theory. Now, my topic today, this was just a kind of introduction, so my topic today is try to analyze random graphs from a class in which you don't have these independence. So there is some kind of global constraint. And here are some examples of typical and significant global constraints. So the first one would be to be irregular. So all the vertices have the same degree. This is clearly an interesting class, or being bipartite, or triangle-free means not containing a triangle, or maybe not containing a cycle, or, as we'll talk later, being planar. But in these cases, well, it is no longer possible to draw edges independently, because if you draw one edge, then the next edge could create a triangle or a cycle where before there was. And then, kind of unavoidably, you need some sort of counting, which is interesting for those of us who like to count. And so before, I will present you a few classes and different kinds of countings. Approximate countings, very rough approximate countings, exact countings, very precise asymptotic countings. As you will see, the counting techniques and the results will differ, but essentially there is a counting argument below everything. So let me start with something which again is very classical, and is the class of regular graphs. So as I said, is it okay, the micro? Yeah. As I said, a graph is irregular if all the vertices have degree d. And then about 30 years ago, or maybe more, a nice model came up for analyzing random regular graphs. And this is the pairing model, sometimes also called the configuration model. And what you do is you have n boxes, n groups, each of them with d half edges. Well, these half edges, they are distinguishable, and the boxes are also distinguishable. So in total, so this is example n equals 4 and d equals 3. So you have in total dn, in this case 12 half edges, and you just pair them. You take a pairing or a matching of them. And here is one example. So this is paired to these, and this is paired to these, and this is paired to this. And now each box is meant to represent a vertex. So what you do is you just, the vertices in a box, you contract them, you identify them, and then it projects into something which is regular. Because every vertex had 3 outcoming half edges, so it becomes 3 regular in this case. However, you see that, for instance, you can get a loop, because a vertex could be merged to another vertex in its own cell. Or maybe you can get parallel edges, and here you have parallel edges. But still, this is a very good model, and let me give you a reason for that. Again, probabilities of elementary events are reasonably well computed. So, which is the total number of pairings? That's an elementary question. In how many ways can you pair Dn objects? Well, this is this odd factorial, because the first object can be paired with 2n-1, the second 2n-3, and so on. And how many pairings contain a given edge? Well, if an edge has already been fixed, you only have Dn-2 objects to pair. So it's going to be this number. And then you take the quotient. Okay, we are doing probability through counting. So this is the total number of pairings, and these are the pairings that have one more. And the quotient is this one. So you see, you can compute exactly the probability that an edge is present in the pairing model, but then you can also then compute these probabilities, and they project quite well to the graph model, which is the one we are interested in. And for instance, the probability that n given edges are present is about this. This is for m constant. When n grows with n, then something different is needed. And for instance, using just this plus a little bit more, I mean the method of moments, which is a basic tool in probability, for instance, you can compute that the number of k cycles that you obtain for fixed k is asymptotically, has a Poisson distribution with this parameter, and the number of 1, 2, 3, up to a certain number of cycles, they are asymptotically independent Poisson. So immediately you can compute the probability that the graph is simple. Because the probability that the graph is simple is that there are no 1 cycles that correspond to the loops, and no 2 cycles that correspond to the double edges. And you just take the product of these 2 Poisson probabilities, you add the exponent, and you turn up with this number, which is quite remarkable. And an immediate consequence, which is a highly non-trivial consequence, is that you can estimate very well the number of regular graphs, because you just take, the number of pairings times the probability of being simple, and this quotient is because when you take these d-half edges and you permute them, they give the same graph. But the good point is the simple graph appears exactly in d factorial to the n pairings. So this quotient gives you the asymptotic number of d regular graphs. And this fact that you can somehow, I mean, it's not so easy as in the binomial model, you see. I mean, there are more dependencies and the model is not so direct, but still you can compute well probabilities, and this has led to a rich theory of random regular graphs over the last 30 years, and now we have fantastic results on the chromatic number, the existence of Hamilton cycles, the size of independent sets in random regular graphs. It also applies, it does not need to be regular, just you fix the degrees of the vertices and you put as many half edges in each box as the degree indicates. This is for d constant. For d growing with n, I mean this is the sparse case, but also the dense case when d can be linear in n. I mean this is more technical, and many people, some of them in this conference, have contributed to this theory. Nick Wormal, Brenda McKay, Mika Prigadevich was speaking the other day. So this is a big area, but I will not say much because this was really as a kind of presentation of the material. So what is next? Next is this example, which are free graphs that contain no triangle. Well, the first trivial observation is that these include bipartite graphs, because a bipartite graph has no whole cycle, and in particular, has no triangle. Of course, there are many triangle-free graphs, which are not bipartite, they contain C5 or whatever, but it was proved some years ago that almost every triangle-free graph is bipartite. And how was this proved? Well, it was proved that if you take a triangle-free graph, which is not bipartite, then this proportion is negligible. So this says that in the limit, you can approximate very well random triangle-free graphs by random bipartite graphs. And for random bipartite graphs, you also have a kind of binomial model. I mean, you fix n1 vertices on the left, n2 vertices on the right. The probability of an edge across is p, and this gives you a model of a random bipartite graph with fixed size on the color classes. And in fact, the typical bipartite graph is going to be quite close to half and half and probability 1/2. I mean, it does not need to be n/2. So this, more or less, this says that we have a good model of random bipartite graphs in which we can compare what happens with random triangle free graphs. This was later extended by Colaitis, and Rothschild in a more general result. Every KT free graph, almost every KT free graph is t-1 part I. Then there was even later extended by Prevel and Angelika Steger. They found a condition on a graph such that almost every H-free graph is partite in this sense, and this condition is that there is an edge which is color critical. I will not go into that. And this has grown into a theory, and now there are recent papers on which is the typical structure of H-free graphs. It could also be, if you forbid H as a subgraph or as a induced subgraph, and this is strongly connected to extremal graph theory, as you may know. But again, this is the end of this example here. But this is a wide area in which there is recent progress and very attractive area. But you see, this is a different kind of counting. You don't have a model like the pairing model. It's a different kind of counting. You have to discard everything which is not supposedly to be in your class. And the last example, and I'm getting home now, is the class of trees. I will speak of label trees, and we all know what is known as Cayley's formula for the number of label trees on n vertices, which is n to the n-2. Okay. There are many proofs of this beautiful result. The one I'm going to offer here is not the nicest, definitely, but it's the one that hints into the direction of the tools we are going to use. And it is the following. So first of all, I prefer to consider rooted trees, because life is easier when you root a tree. So here is the tree is in the root is in red, and I denote by Rn the number of rooted trees. Well, since labels are distinguish the vertices, the number of rooted trees is going to be n times the number of unrooted trees. So these quantities are almost the same. And now I build a generating function. This is a power series with coefficients Rn. There is an n factorial in denominator. This is called the exponential generating function. And this is because our objects are labeled, otherwise it would not be here. You're probably more used to the ordinary generating functions in which there is no n factorial, but in this case we do that. In a formal level, one is the Laplace transform on another, but we don't need to go into this. And now, here is the fundamental equation, which reflects the combinatorial decomposition of trees. So, a tree, there is a root, and there is a collection of sub-trees attached to the root. And this equation is really indicating this. A tree is a root, and a root has only one vertex, so it is encoded by x, times an unordered collection of trees, because the order of the children of a given node really do not matter. So either there is just no child, one child, or k children, and in this case you have to divide by k factorial because of the ordering. And of course this is the exponential. So this generating function satisfies a functional equation, which is in this case is a very simple type. And if I write this like this, you observe that this function is the functional inverse of this elementary function. And then you apply Lagrange inversion theory, okay, which tells you how to compute the coefficients of a function in terms of the inverse, right? And then you just do Lagrange inversion, which is an elementary exercise, and you get this formula, which is okay, because now if you want to get the total number of trees, you have to multiply by n, which is the possible number of roots. So you see, trees decompose nicely, and this decomposition translates into equations satisfied by the generating functions. So these equations can be either algebraic, They would be algebraic if they were unlabeled, or you can have some exponential functions, or some trigonometric functions, or even some Bessel functions, but essentially the combinatorial decomposition translates into functional equations, maybe differential equations, because sometimes you have to differentiate. And the goal now is to analyze these equations. In a few cases, and this is the only case in this talk, we can find the solution exactly. But even if the equation is too complicated to find the solution exactly, we can really say a lot of things from the functional equation satisfied by the geometric function, as we are going to see in a moment. And the key idea is that the same method allows you to analyze parameters in trees. And I have chosen two basic parameters. The easiest one is the number of leaves. A leaf is a vertex of out degree 0, right? So a leaf is a vertex like this. Here there are 5 leaves. So we want to understand which is the typical number of leaves in a random tree. And then what we do is that we say R and K is the number of trees with n nodes and k leaves. So we refine the enumeration, and with the generative function, what we do is we enrich it, adding a new variable y. So here is a bivariate generating function. You see there is an n factorial here because the vertices are labeled, but the leaves do not carry extra labels. So on the leaves is ordinary, on the vertices is exponential. And now I rewrite the former equation. So the former equation was this. When does a leaf appear? But a leaf appears when from an ode I do not select any descendant tree. So this one here, which was the empty collection of trees, has to be replaced by this one. And again, you get a functional equation. And as we'll see later, from this functional equation, you can get a lot of information just from this functional equation that essentially solves, in some sense, the enumerative problem of counting trees according to the number of leaves. That's an easy parameter. A not so easy parameter, but very fundamental in computer science, for instance, is the height. So what is the height of a tree? Is the maximum distance from the root to a node. It's how deep is the tree, right? So this tree has height 3 because these are at level 1, level 2, and level 3. This is a more complicated parameter because it's an extremal parameter. It's the maximum height, possible height of a node. But still, suppose RH is the generating function encoding trees with height at most age. Then what we have is this recursion equation. This equation here says a tree with height at most age consists of a root and a collection of subtrees of height at most h minus 1, because the subtrees have height 1 less than the original tree. So for instance, R3 is going to be this beautiful entire function, which is a tower of exponentials. It looks difficult. Well, it is not easy, but this can be analyzed using analytic methods. And if you are really interested in trees of height h, well, you only have to subtract from here, and you get the trees that have height exactly h. Now, what you do is you take these equations among the generating functions. Instead of consider them as formal power series, you look at them as analytic functions, either of one variable or two variables. And these analytic functions can be entire, like here, or can have singularities. You can check here that this function R of x has a singularity of 1 over e, so it's analytic only on a disk of convergence. You can also see how the analytic function behaves near the singularity, and then you can estimate the coefficients, which is the thing you are interested in, by Cauchy integration with carefully selected contours around the singularity, or maybe using the saddle point method or other techniques available from complex analysis. And in this case, what you can prove using analytic methods is that the number of leaves is distributed asymptotically like a normal law. The expectation is n divided by e minus 1 to the n. the variance is linear, so the fluctuations are of order square root n. So a typical tree will have really n over e leaves with Gaussian fluctuations of order square root of n. You can prove even much more. You can prove much stronger concentration results, large deviation results. But more generally, this is for Aug degree 0, but the number of vertices of Aug degree k, again, is asymptotical normal with this expectation. You can prove these analytically. Well, I give you just a kind of heuristic idea, because you can really see that these label trees correspond to branching processes, Galton-Watson trees, with this offspring distribution, which is Poisson, conditioned on the total size being n. And this is the reason behind this result. And with respect to the tree, I think it was first, I understand, proved by Remy and Segeres, that the expected height of a random tree is the square root of n, exactly with this constant. Okay? This has been refined, and now we have a result that tells you not only the first moment, but all the moments and the distribution. And the distribution of the height is quite tricky. I mean, you may imagine it's an extremal parameter, it's not an easy parameter, and it involves some theta function, but it has been completely obtained. Well, Flageolet and Otlisco and other people have worked on it. So now we have a very good description of the height of trees. So this is a typical linear parameter which follows a Gaussian distribution, like in many additive parameters. Additive means that the number of leaves in a tree is, you sum up the number of leaves in every subtree. This is an extremal parameter which typically tends to be more complicated and to give rise to more complicated laws. So with more effort you can analyze it. And here the idea, and if you were this morning at Jean-François Legal talk, I mean, the trees are kind of connected with random walks. And the typical height of random walk is square root n, which is responsible for this square root n here. So the conclusion is that random trees can be analyzed very precisely. The degree distribution, the profile is how many vertices, how many nodes are at a given height. And this is the vertical profile. You can also do with more work the horizontal profile. This applies also to unrooted trees and other variety of trees. And it applies to forests, which are collections of trees. And the recent monograph by Michiel Dermot on random trees tells the story and gives many results. It says that connections to Brownian motion and all kinds of things. So now we come to the second part of the talk, and our next step will be, well, to use these ideas from trees to go to let's say, a more complex class of graphs, which are planar graphs. Of course, trees are planar, but they are not a good representative of planar graphs. And they are more complicated, but the key point is that still they admit the compositions which are very much tree-like. I mean, the kind of decompositions and the kind of the equations you get, they are qualitatively of the same kind as we have seen, but more involved, with more machinery and maybe with more complicated singularities, but they really look like this. So the starting point is the enumeration of maps. Again, this was present in the talk by Legal this morning. And so a map is a planar graph with something else, together with an embedding. So it's a connected graph embedded in the plane. You allow double edges and you allow loops. And this theory was started by Tad about 50 years ago. And well, Tad decided that it would be good to root the maps just as the same way as you root the trees, because the analysis is simpler. And then he found out the best way to root was to root at an edge and to give this edge an orientation. So this is a kind of reference point. And the good point about rooting is that now every edge, every vertex, every face is distinguishable with respect to the root. So essentially this routing kills all possible automorphism. And then Pat proved the following fantastic formula, that the number of rooted maps in this sense with n edges is given by this exact formula. If you just do a Stirling approximation and you work out the asymptotics, you see there is an exponential growth, which is 12 to the n, which comes from this 3 to the n and 4 to the n here, and a sub-exponential growth, which is minus 5 over 2. If you like counting, you may have recognized the Catalan number here. Okay, so it says that the number of maps is the number of, let's say, binary trees times 3 to the n times. Well, this was made explicit by Gilles Schaeffer some years ago, and he proved, using ideas of Cloquy and Vauquelin, he proved, gave a combinatorial proof encoding maps through trees. Well, I mean, you know now there are many bijections in combinatorics. Some are more beautiful than others. This one, to me, has the merit of being beautiful and incredibly useful. I mean, this bijection is the one that, as we saw this morning in Jean-François' talk, allows to study the metric dimension, the metric theory of random planar maps, and to talk about continuous random planar maps. Okay. And then, okay, here is the original paper of Todd. I think this was also really a fundamental paper. He wrote a series of papers, and they were called a census of triangulations, a census of planar maps. So he wanted to censor all these things. And still, this is nice reading, this paper, even if always Todd uses his particular terminology. Okay. Well, you may know that Todd was one of the greatest graph theorists of the last century. He did many things, and among them, he started the theory of map enumeration. And then what he did also, in this same paper from 1963, I think it's a Canadian Mathematical Journal, is he studied maps with a given connectivity. So our maps were connected. Now you know that a graph is too connected if not only is connected, but has no cut point. So removing any vertex, it stays connected. It is 3 connected if it is even more. Removing 2 points, it stays connected. And then, what did that, using the decomposition of a graph along 2 and 3 connected components, let me just briefly give you this example here. So this graph here is not 2 connected. This is a cut point, and this is a cut point. So it has 3 2 connected components. But you see, there is a canonical decomposition of a map into the 2 connected components, so you can relate the generating function of one to the other. And if you know the solution to one problem, then by substitution, you get a solution to the other problem. I will not go into 3 connected components because it's technically more complicated, but this is the idea. And then for 2 connected maps, there is again a closed formula. For 3 connected, there is no closed formula, but I give you here the asymptotics. So this is the asymptotics. The exponential growth depends on the class of maps. This is 12 to the n, here is 27 over 4 to the n, and here is 4 to the n. But what is important is that this exponent is always the same. So there is a kind of universality that all naturally defined classes of maps have this exponent. And this has some consequences on the structure of random maps. By the way, when you get to the 3 connected maps, then you can recall Whitney's theorem. And Whitney's theorem says that if you have a planar graph which is 3 connected, there is essentially only one way to draw it in the sphere. It has a unique embedding in the sphere. Okay? Here is one example. The nice pictures are from internet. The ugly pictures are mine. Because this is also related to the famous Stein's theorem that says that every 3 connected planar graph can be realized as a skeleton of a 3 polytope. So here is a 3 polytope realizing something. Okay? But once you are here, okay, there is an equivalence between 3 connected planar graphs and 3 connected planar maps. And this is the hint, and this is the starting point. What I find surprising is that it took so long to establish this connection and start going from map enumeration to graph enumeration. And this was first done by Bender, Gao, and Wormal, who had a fantastic record in the field of map enumeration and many others. And they realized that you could use this fact to enumerate two connected planar graphs, just by looking again at this decomposition into two connected components. So they really opened the way, and we followed suit. And then, I mean, they stopped here because there were some technical problems. We were able to solve these technical problems and complete the enumeration of planar graphs. I will not give you the details, and will be grateful for that. But just let me tell you the basic things. So the basic things is that if Gn is the number of planar graph with n vertices, and our graphs are always labeled, then this exponential generating function is explicit. Well, it's not easy, it's long to write, but it's explicit just in terms of elementary functions. There is nothing more than some basic algebraic function that comes from the enumeration of planar maps. These are fourth degree algebraic function, combined with some implicit equations and some exponentials of log. So this is really explicit, and you can compute. And in particular, you can give a precise estimate of the number of planar graphs. It has well, there is an n factorial here. There was no n factorial before because the objects were not labeled. Now they are labeled. And this is, let's say, the exponential growth, which is a certain constant that you can compute. And well, the exponent is -7/2 because maps are rooted, so there is an n factor additional. But this -7/2 is just -5/2 times n, nothing more than that. And in really, the inverse of this growth is the radius of convergence of this series. So once you have a series explicitly, you can prove that it is analytic in a certain disk, and you can compute the radius of convergence, and this is what we do. Okay. And then you can analyze random planar graphs. Let me tell you that the uniform model was first introduced and analyzed by McDermott, Steger, and Wells. They obtained a number of interesting and substantial results without the use of generating function. It was really based on double counting and ingenious combinatorial and probabilistic arguments. Now, these results here, they are used using analytic tools, which give a lot of precision. So nowadays, we have a good picture of what is a random planar graph. We know that the number of edges is asymptotically normal, and the expectation is 2.2. It has to be between n and 3n, right? 3n because this is the bound for planar graphs, and n because a large proportion of them are connected. The number of connected components is just, it's just 1 plus some small components that are responsible for this Poisson distribution. The largest component, okay, is not a giant component. It's really everything minus a few points. So it's really a super giant component. The largest block, and here we have a phenomenon more similar to the largest component, is linear in size, almost surely. And it's interesting because the distribution of the largest block follows a continuous but not normal law related to the Airy function with fluctuations instead of square root n to the 2/3. For each k, the number of vertices of degree k is linear, and this gives you indeed a discrete distribution for the degree distribution. And this function is explicit, but I think it took us about 4 pages of later to write it down. The maximum degree, and this is something very recent, we established with some people here, that it's log n with a given constant, and it's really concentrated on log n. The diameter is about n to the 1/4. This is very much related to the diameter of random planar maps, but here we have less precise results. So these results are due with Jimenez and Michel Delmota, and some of the results, particularly this one, is with Costa Panagiotou and Gerika Steger. So there is a variety of authors that we have worked on this common project. Now, let me just give you a small, how long do we have?
6 minutes.
6 minutes, okay. So maybe I will skip this one. Okay. Now we can move to graphs on surfaces. I mean, planar graphs are graphs on the sphere, and we can ask about graphs on surfaces. And recently, it was proved independently by 2 teams that the number of graphs of genus G that can be embedded in a surface of genus G is asymptotically this thing here. So you see, this gamma does not change. The exponential growth does not change. The only thing that changes is the sub-exponential growth. This was known for maps, and essentially what we did was taking the starting point on the enumeration of maps on surfaces and work it out. I mean, quite technical. And the important thing to me is that we also were able to analyze random graphs of genus G, and qualitatively there is no difference. The distribution of the number of edges, the number of components, the largest block, the largest component is exactly the same. So if we do the following experiment, okay, you fix a genus, let's say 20, and you give me random graphs from this genus and tell me which is the genus. If I just look at these statistics, I cannot tell. I really have to go into the graph and compute the genus of the graph, because macroscopically they are indistinguishable from planar graphs. And the last thing is that, well, graphs on surfaces are one of the fundamental examples of graph minors, right? So let me just briefly tell you about graph minors. So a graph H is a minor of G if H is obtained from a certain subgraph of G by contracting edges. So you take G, you just throw out some part of the graph, and then you contract. It's a more general notion than that of subdivision, and as you may know, this has become one of the greatest theories in the last decades. And a class of graphs is said to be minor closed if it is closed under taking minors. So with every graph, every minor is also in the class. And the foremost example are graphs in a given surface. Because if you have a map embedded in a surface and you contract an edge and you do it carefully, you do not destroy the embedding, so it is still embedded in the same surface. Of course, the main result is Robertson's single theory that says that every minor closed class is defined by a finite number of forbidden minors, one of the main results in mathematics. But we don't need that. Just an example, Kuratowski theorem tells you that planar graphs are those that forbid or exclude K5 and K33. Now, in the last year, there are several results on random graphs from minor closed class, and some of the properties that we have for planar graphs are shared also for these classes. Let me recall you that if a class is minor closed, it is sparse. It has at most a linear number of edges. So we are always in this sparse setting. We are never dealing with dense graphs. The results are less precise than the one you have with analysis, but more general. And as an illustration, let me give you this series of results of Colin McDermott, who is now producing a series of beautiful papers on this area. If you take a class of minor closed and you add some technical condition that Colin calls addable, but just think that the excluded minors are too connected, then there are some good results on the structure and number of connected components. So the number of connected components is 1 plus some lambda, and we get saying something about this lambda. The largest component, again, is almost everything. The complement of the largest component, which is a discrete graph, follows an explicit discrete distribution called Boltzmann-Poisson distribution. And for each fixed H, there is a linear number of pendant copies of H. A pendant copy is a copy of this small graph H, which is attached to the rest of the graph by a single edge. But we have no results on the distribution of edges, no results on the largest block. Very seldom we can have the generating functions and do the asymptotic analysis as we did before, but these results, as you see, are applying more generality. And I want to finish with an open problem, and it is the following. Remember this statistic, which is the size of the largest two connected component, the largest block. Well, I said for planar graphs it's linear, and it's okay. But for a very special subclass, which are called series parallel graphs, this is small, the largest block is logarithmic. And this was analyzed independently by these two groups of authors. Now, what I think is responsible for this log n is bounded tree width. So my conjecture, or what I believe is true, is that if a minor closed class has bounded tree width, then the largest block is sublinear. I do not dare to write here log n, but I think it will be sublinear. And as you guys know, one of the fundamental results of Robertson-Seymour is that at least one of the excluded minors is planar. In every case when we have been able to compute everything, this turns out to be true, but this is a conjecture. And the first open case would be exactly the class of tree width at most k. Tree width 2 is series parallel, though this is done, but already from k on, we don't know how to do it, because we don't know how to count precisely graphs with a given tree width. And I think that's all, and thank you for your attention.
Thank you, Mark, for an intensive overview of various random graph models with global constraints. Are there questions or comments? So if not, I have indeed quite a few. You start with random graphs with a given number of vertices and edges. In particular, you mentioned the evolution of random graphs with a given number of vertices and edges. As far as I see from your slides and talk, you talked about random planar graphs and other structures on n vertices only. And in particular, you talked about the size of the largest component, which is of linear size, n minus little of 1, which is in a way corresponds to the very stable late stage of the evolution of random graphs. What can you say about the random planar graphs with a number of vertices and edges in terms of evolution?
Well, you can probably say more than me, because you did this work with Thomas Muscher, and the 2 steps on the evolution of planar graphs. For triangle-free classes, for instance, Angelica and other people really studied very much what happens with the number of edges varies. But indeed, we are limited. Well, we can do the dense case. I mean, we can do the stable case. I mean, you fix the number of edges in a planar graph. This maybe I could have mentioned. And the number of edges is about alpha n, where alpha is between 1 and 3. We can compute things using the local limit theorem, and really qualitatively nothing changes. So.
Another question is, you had this beautiful theorem on the number of graphs on a given surface with a fixed genus. And of course, it's a beautiful theorem, but one might wonder whether one can get the kind of interesting result when the genus is linear in n or logarithmic in n. Is there any hope? What could be an obstacle?
This has not been done for maps, as far as I know. For maps are special, and you can operate all maps of all genus. But as far as I know, this does not give you tools for letting the genus growth with n. It might be, but I haven't seen that in maps. So if it is not done in maps, then it's better not to try.
But I think for the triangulations, we do have a wonderful theorem by Chapuis and others when the genus is linear in n.
Well, I'm not aware of that.
Okay, thank you. Are there more questions or comments? Yeah, Alan? I have done that.
Yes, the chromatic number of a random planar graph is 4. It is at most 4, and almost truly it contains K4. Now, the interesting thing, if you ask me about the chromatic number of a random graph of genus G, we know it's either 4 or 5, because a random graph with a large enough phase width, it's 5 colorable, and we are convinced, at least Boy and Mohar is convinced, it has to be 4, but we cannot prove it. So the only aspect where there would be a difference between planar and genus G is this chromatic number, but we are sure it has to be 4, just we cannot prove it.
Do you know the length along this path?
That's a good question. I have a conjecture saying that the length should be linear. I can prove it for 3 connected using Taft's theorem on 4 connected graphs, but I can't just do it for. That's a good question. That's my conjecture is not only a path, but there is a cycle of linear length, but I cannot prove that for the moment.
And Brandon? Louder. Louder, please.
Well, or maybe a microphone will help.
Two other classes that you might have mentioned, but I might have is an unlabeled case, and the other is graphs which are planar in that there exists an embedding, but you're not counting different embeddings separately. I wonder if you can do anything with those problems.
Well, for the unlabeled, I think there are several people working on this direction, but there are some problems with the enumeration of symmetries. My understanding, talking with the French school, is that if they can manage the symmetries for the three connected graphs, they could go and translate. They have done it for simpler classes of graphs. So my understanding is that in the future we'll have an enumeration of unlabeled planar graphs. I'm sure no qualitative behavior is going to be different. Okay? And the second is about the number of embeddings. Well, I'm not sure I understood completely the question.
So you can count graphs, abstract graphs, which are embeddable in the plane, and that's a different problem from counting the number of embeddings in the plane, which is what you're doing.
No, I'm doing unembedded graphs. I mean, line graphs do not carry an embedding.
Oh, I'm sorry.
Yeah.
Missed that.
More questions or comments? Otherwise, let's thank Marc for wanting to talk. And Keith from the local organizing committee.